this is an example where we're going to do availability analysis. It's a closed system. We have steam contained in a piston cylinder. We have the initial state of the steam at 500 kPa and 300 degrees C. We're going to have a constant pressure process where we reach equilibrium with the surroundings, which is at 30 degrees C. And so if I look at this at a constant pressure process on a TV diagram, or TS diagram, here's the line of constant pressure. We're starting here, we're going down, and basically we're ending up here. So we're going from state 1 to state 2, and it looks something like that. So we've looked at this, and so now, before we get started with the analysis, let's look up the various properties that we have to have. So U1 is 2802.9. V1 is 0.52272. H1 is equal to 3064.2. S1 is equal to 7.4592. So this we just look up in the superheat tables. And then at this state we have a subcooled liquid, so state 2. So I know that U2 is equal to U sub F at 30 degrees C. So that's equal to 125.02.05. V2 is equal to V sub F at 30, so that's equal to 0.001004. H2 is equal to 125.06, and that's equal to H sub F. And S2 is equal to 0.43278, and that's equal to S sub F. So we look up all these properties. And so we would be interested in finding Q, and so we know for a constant pressure process, well, perhaps I should back up. So now we're going to always look at this with the methodology we have for first law analysis to find the first law terms. And so we know it's a closed system. The substance is water. The process is P equals C. And we know for a closed system P equals C that Q is equal to H2 minus H1. So we can find Q is equal to minus 2939.1 kilojoules per kilogram. I can find the change of internal energy, delta U, is equal to U2 minus U1. And so that's equal to minus 2677.85. I can find W two different ways. I could use the first law analysis, so I could use Q is equal to delta U plus W, and I can find W, I know these two terms, I can find W, or if you want, W is equal to the integral of P dV. P is constant, so it's P times V2 minus V1. Whichever way you do it, you'll get the same result for work. And so we get that the work is equal to minus 261.25 kilojoules per kilogram. And so now what I want to be able to do is to find the change of availability. So we wanted to find all these terms just to see how to do it, and then I can find the change of availability per unit mass. And I'm going to erase this, and we'll determine that. So A2 minus A1, So I'm using a lowercase a because we're doing it per unit mass, so it's, do it here, a is equal to the large A divided by m. So I have, this is equal to U2 minus U1, so we're using the expression we had before, plus delta KE, plus delta PE, plus P0 times V2 minus V1, minus T0 times S2 minus S1. And we see that these terms go out. So we don't have those terms. And now we just substitute in, and we find the change of availability. So A2 minus A1 is equal to 125.05 minus 2802.9 plus 100 plus 500. No, P0 is 100. I sometimes have trouble reading my own notes, so that's what happened there. Times V2, 0.001 minus V1, 0.5227 minus T0, 300 times S2, 0.4328 minus 7.4592. So what we want to do is add and subtract all these things, and we come up with that A2 minus A1 is equal to minus 622.12 kilojoules per kilogram. So what does this tell us? It said the work potential of the water at the end is less than the work potential of the superheated steam at the beginning. And you're saying, thank you very much, but now I have a way to quantify what it is. Intuitively, you would say, I know that this has a higher work potential. Now we have a way to calculate what the change is. So this is one example. Now we'll do another example, which builds on example 9.3 in the text, but I'm doing it a slightly different way. So this is example 9.3. And in the text, it turns out that you need to have a computer program for the steam tables to do it. It's a real nuisance, or you have to do it trial and error, which is another real nuisance. And so what we have here is we have a tank of water. So we have water, it's at 300 degrees K, 27 degrees. We have a piece of steel. The steel has a specific heat, C is 0.5, and it's at 1200 degrees K. And this is 50 kilograms. So basically what's happening is I take this steel that's hot, it's quenching, and so you could quench the steel and you can change its properties. So you do this if you want to make steel more rigid. So anyway, I take this hot steel, plunk it in the water. The water and steel will reach thermal equilibrium, and they'll both be at the same temperature. And what we want to find is the irreversibility associated with this. So now we're interested in the irreversibility. This has a very high work potential. It's very hot. And let's see, it's 5 kilograms. So this is very hot at 5 kilograms. This has a low work potential. It's 27 degrees Celsius. It's not much of a work potential. I'm going to plunk it in. And what we can say for water, the C for water is approximately 4.2 kilojoules per kilogram degree K. So it's 5 kilograms. And so now what we do is we can represent the internal energy. U is equal to mCT. So I can have this for U1, so I can let this be 1, I'll let this be 2, and then the equilibrium be 3. So this is, M is 5 times 0.5 times 1200. So that's 3,000. And U2 is equal to MCT2. So this is for the steel and this is for the water. So this is 50 kilograms times 4.2 times 300. And this is going to be equal to 63,000. So it's a much bigger number. And then the final temperature, we have U3 is equal to U1 plus U2. So now this is going to be at state 3. So this is equal to 5 times 0.5 times T3. The same equation except it's at a different temperature, plus the same deal for water, 50 times 4.2 times T3. And this is going to be equal to the sum of the two energies, so we have 66,000. We solve for T3, and T3 is equal to 310.6 degrees K. So we're able to find out what the equilibrium temperature is, so it's an easier way to do it than using the steam tables. Now what we're going to do is that we found the final temperature. We're going to look at the entropy change for the water, the entropy change for the steel, add them together to get the entropy production, as we did in chapter 8. Del S of the water is, and we're using this solid methodology that was mentioned in chapter 8 for incompressible substances and not using the tables, is MC times the log of T3 over T1, or it could be T2 actually, is equal to 50 times 4.2 times the natural log of 310.6 over 300. And so I get the change of the entropy of the water. The entropy increases, and this is 7.292 kilojoules per degree K. I'm going to do the same thing for the steel. Del S of the steel is equal to MC log of T3 over T1 is equal to 5 times 0.5 times the log of 310.6 over 1200. And if I do that, this turns out to be del S of steel is equal to minus 3.379 kilojoules per degree K. I'm going to add these together, so the entropy production is the sum of the del SI. So del SP is equal to the sum of the del SI. So if I add those together, I'm going to get, this is plus 3.913 kilojoules per degree K. And then the irreversibility I is equal to T0 times del SP. So it's 300 times 3.913. So this is equal to 1174 kilojoules. So a huge irreversibility, which we'd expect because this is very hot and it's losing almost all of its work potential. The work potential of this increased from 300, which is T0 typically, to 310. So there's a very little increase of the work potential of the water. There's a big decrease of the work potential of the steel. and that's manifested in the amount of the irreversibility. So that you have some practice doing problems and not just watching me do problems, look at the following for homework. 9.1 ABC, 9.12, 9.15, 9.16.